So we will start this webinar now. So hello everyone, and welcome to this PowerSys webinar. For a bit of context, let me first introduce you to PowerSys. So we are a global electrical engineering software and services provider. We offer fully customized solutions to help our customers solve their complex electrification challenges in EV and grid. Our solution includes electrical engineering expertise, simulation software, and power computing. And for more than 20 years now, PowerSys has been delivering its expertise to thousands of customers all around the world. And in 2023, it became the exclusive worldwide distributor of SIMBA. So during today's webinar, we will be discussing the design of a DC-DC Full Bridge LLC resonant converter by using SIMBA Python API for battery charger applications. It is my pleasure to introduce and give a warm welcome to our speakers for today. So first, Guillaume Fontes. Hi, Guillaume.
Hi, Stephanie.
Guillaume became a co-founder of SIMBA in 2020. He's an associate professor of power electronics in the National Polytechnic Institute of Toulouse in France, and a scientific advisor for SIMBA. And secondly, Anup Kumar Singh. Hi, Anup.
Hello, hi, Stephanie.
So Anup received his PhD degree in the field of power electronics in November 2021, and he works at PowerSys as a power electronics and application engineer and a member of the development team for SIMBA. So just lastly, all questions will be answered during the Q&A session at the end of this webinar, and you will also receive a short questionnaire at the end of this session. So we thank you in advance for all of you who will take the time to give us their feedback, because it's very useful for us to better develop our webinars. And without further ado, please join me in welcoming Guillaume.
Yeah. Thank you, Stephanie, for this introduction. So first of all, let me remind you what's SIMBA. So SIMBA is a new generation of power electronic simulation software that minimizes the entering time required to design battery converters. Basically, there are different ways to use SIMBA. First one, I would say a classical, which is based on the graphical user interface. This is the desktop version. A second one is to use a web browser to play with an online version. And at last, a third one, which is, according to us, the most powerful way to use all the potential of SIMBA is a Python API, a Python module, actually, to run Python scripts or Jupyter Notebook and to get all the power of the system of different Python modules. And that's how, in our last webinar, we showed this kind of use case to get an efficiency map of a dwyer inverter by taking into account the power switch losses. In this example, we showed how a Python script was able to run more than 200 simulations of different operating points in around 5 minutes. And today, we will show you how to use the same powerful feature to design an LLC converter, which can be a holster. To set the context, let me remind you that the LLC converter uses the switching frequency as a degree of freedom to transfer the power, that's to say, to set the voltage gain. And the main challenges to design an LLC are to get a large gain range, of course, but also with a frequency range as narrow as possible and a high magnetizing inductor to get high efficiencies. So the design process can be complex and painful, mainly because of the difficulty and the required time to evaluate the design parameters on real waveforms. And here, we are going to show you how to solve this issue with a Python script, which is able to evaluate the design parameters influence on real waveforms by launching a huge number of simulations. But before showing you this, let me show you the classical approach and the basic principle of the LLC. There are three modes of operation of a LLC converter. Below the switching frequency, around the switching frequency, and above the switching frequency. The last two modes of operations are usually preferred as they allow ZUS operation, for example. But around the switching frequency, waveforms are close to sinus waveforms, which usually leads to follow a conventional design approach based on the first harmonic assumption. The idea here is to consider a simplified model of the resonant tank of the converter with the inductor, with the resonant inductor, the magnetizing inductor, and the resonant capacitor, and a resistance to get a first transfer function of this simplified model. The second assumption is to consider that the main part of the power is transferred with only the first harmonic, and that the global design is equivalent of the AC gain with the first harmonic assumption model. Then this expression of the gain can be a little bit simplified, and we've got here a gain which depends on the normalized switching frequency, the inductance ratio between the magnetizing inductance and resonant inductance, a quality factor which depends on an equivalent load resistance. And this equation will be typically used in most of conventional design approaches to get the maximum mutual gain depending on the quality factor, which is shown here on this graph. From these curves and from the minimum and maximum gain, which can be computed for the converter specification, the first set of values of the inductance ratio and the quality factor can be chosen. And then, according to these values, the gain and the frequency have to be considered and to be checked to check if they are within the limits. So if it's the case, then the different values of the resonant tank can be computed and the design process can be kept on. But if it's not the case, another set of values for the inductance ratio and the quality factor must be chosen to get the required ranges of gain and frequency. So here we have an iterative process, which is more or less painful, depending on the approximation made on the first harmonic assumption. So now Anup will show you how to get rid of this approximation to limit or even avoid this iterative process.
Thank you, Guillaume, for a nice presentation on the theory part. So, okay, I'll share my screen now. Okay, so I'll be taking how this, the iterative approach can be minimized with the help of, time domain simulation approach. So if to sum up the process with the conventional that Guillaume explained, so why there's a need to go for the modern approach. So what used to happen in the transfer function approach, so you calculate the frequency domain, the transfer function which is done in the frequency domain, and then you calculate the peak gain curves and resonant curves. From there you calculate peak gain curves, and then you go you'll get initial tank values. So why it is called initial tank values? Because you have done approximation from the frequency side. So because to get the transfer function, you have to approximate it to the first harmonic of that. So but in actual it is a, in time domain it is a switched model. So the input to the resonant tank circuit will be of the square in nature. So if you operate the circuit at resonant frequency, it will be exactly same as you have made the approximation. But to counter with the line and load regulation, if you move away from the resonant frequency, the curves will deviate. So there it comes, the iteration. So you get the initial tank values. So then after getting these tank values, you iterate the simulation to get the actual curve to further tune your tank values. So there, to select final tank values, you do iteration on either you prepare a model in simulation or you prepare a prototype of that, and then you do the iteration to reach to the final tank values. So this process will be maybe the little bit time consuming. So to avoid all these things and to avoid to get your final tank values, so let us say it is not initial tank value, we can say it will be if you get the final tank values at one shot itself. So how will you do that? So that is very easy. I mean, if you understand the basics, like first of all, you need to create the model. So then after creating a model, the second step will be you have to get the curves in real time without any approximation. So you have to get the curves from the time domain, from the simulation, from simulating, from doing the simulation in the real time, and to get the curves and plot it, and then you can go ahead with the design with your specifications. So but here is a catch: it requires many iterations to get a good to get a good resolution plot. So you may get, based on your specs, based on your designs, it may vary from 6,000 to 10,000 iterations. So which software will support these many number of iterations? And that too, it should save your time. Ultimate goal is it has to save your time. And then but if you if you clear this bottleneck, then you can easily obtain the tank values at once. So okay, let us proceed with the next steps, like how you can do and how you can plot this resonant gain curves in real time domain. Okay, so the first step is model creation. So I can show you some small the model you can create in an open loop. You can see you can add further your further parasitics. You can add ESR, ESL values. You can add diode forward voltage drop to get the good accurate curve for your resonant plot. So that will be that will give you good design design values. Okay, so to test this, you can get initial values maybe using FHA, and then you can test is as Guillaume explained, the 3 mode of operation. So this is the normalized frequency. So let me show you one example, maybe less than resonant frequency, one mode of operation, which is less than resonant frequencies. Resonant frequency here, it is 200 kilohertz. And then after that, you can check the simulation settings. So we have 2 types of solver here. One is predictive time step, and the another one is fixed time step. So predictive time step, if you want more speed, it will be, so for iteration purpose, we have used predictive time step. And there's one more feature called is to stop at steady state. So this feature makes you, it will further save your time. So for each and every iteration, you don't need to define the end time. You don't need to do that. So it will further save your time. As soon as it reaches steady state, it calculates the value and it will save it, and it will be like plotting that particular value. So this is the simulation settings that you need to take care. And then if you run the simulation for this for operation below resonant frequency, you can check it. I mean, after creating a model in the open loop simulation, you can check it whether all the 3 modes are working properly or not. If we check, so I think, okay, let me check. Yeah, so this is okay. Yeah, good. Then after this, if I want to see the curves, the mode, okay, so this is good. So you can see this is the mode of operation below resonant frequency. So this is the current at resonance tank circuit. This in yellow color, the current in the magnetizing inductance, and this is the current in the transformer. So as you can see here, so this is operating at below resonant frequency. So this is you can see as soon as this current through magnetizing inductor and the current in the tank circuit becomes equal, the current in the transformer becomes 0. That means the power the power is not being transferred for this particular interval of time. So what happens at this time, there is a soft commutation at the output, I mean at your diode bridge. So there you can say the ZCS will happen, zero current switching. So in that way, there is a no point of reverse recovery losses from the diode side also. So if you know the theory part, like how ZVS, ZCS, it can be achieved. So it is good to go ahead with this design process. So in this way, you can check the 3 modes of operation, and you can see that your topology is properly working or not. And then in the next step, we can do the we can go to the Python scripting part, and you can call this design to make the number of iterations. So in the next step, it is the Python script. So I have taken the example of 3.3 kilowatt onboard charger specifications, and the parameter that we have to sweep is 8,000 iterations. So earlier it was 4,000 iterations, but because of with the help of parallel computing, with the help of multi-processing, we could able to make it 8,000 iterations with good resolution curve. So that will be seeing how this curve is plotted. From that curve, how you can reach your final design steps. So if I'll go to the scripting part, so this is the script. I'll just explain the structure of the script of Python API. So you can see asim.simba. So this is the Python API. So for our software. So with this software, you can use our feature, and you can call our design what you have made in the Python domain. In other way, you can create a circuit in Python also. That is also possible. And apart from that, the packages that we have used, it all depends on your application, what you are doing. And then here simulation parameters are being defined, and load conditions. So this is the parameter range, sweep parameters. So we have taken the inductance ratio. It is 8 inductance ratio. The load ranges are 10 load ranges from 0.1 to 1. So 0.1 is like it is close to open loop, close to no load condition, and 1 is like it is the load is around 100%. So so if you calculate the iterations, it will be around this will exactly 8,000 iterations you have to do. Then you can define the methods, functions to do the multi-processing, to do the parallel processing. So here you can see we have defined it, and then to plot the curves you can write. So parallel processing we have done using this multi-processing, and then in this way you can go ahead. And one more thing, that the feature that we have used here is, you can see stop at steady state. It is true. So with this feature, for the your time will be saved. You can get the results. You can get the output value, average output value, as soon as it reaches the steady state. And further, you can define the time step in the Python itself. And I can run it now. So, but you can see how much time it has taken to do that. So each run, it calculates the average output, average voltage, which is defined for that particular parameters, because for each run, the parameter, the tank values is being calculated based on the sweep parameters that you have taken. And all the cases are being run in parallel, and each run takes approximately 0.04 seconds. So which is very, very good. And total time you can see here, for 10 core machine, it took around 5 minutes and 24 seconds. So which is very, very good. So if you are getting 8,000 iterations in 5.5 minutes, so this is like, very, very good. We can't say. So it is in 10 cores machine. So for 8 core machine, it took around 7 to 8 minutes. So you can see this is 8,000 cases in 5 minutes, 24 seconds for 10 core machines. So the next step is like after running this, this script. So it took around, for me, it took around 6 minutes, and then it gives the plot or something like this. So this is the plot that you'll get a resonant curve after running all these iterations. So you can plot based on your specifications. You can specify the minimum gain requirement, maximum gain requirement, and you can look at the various curves. So from this plot itself, you will use this plot to make this plot, so which is maximum gain, or you can say peak gain versus quality factor. So this you can get. So this is the plot from where you'll reach your final design. So suppose for your nominal load, your quality factor that you have taken is 0.35, and your maximum gain requirement for that particular specifications, you are having suppose 1.25 is your requirement for peak gain. So you can select the peak gain which is slightly over 1.25. So let us say we have taken 1.3 here, for example, for that particular load, nominal load. So then you can select for what value of ln you are getting this. So let us say for ln equal to 7, we are getting this. And although to avoid interpolation at that particular your requirement, you can further go to script and you can further plot that curve and you'll get this these things. Otherwise, interpolation also in this curve will be good to go ahead with your design. So then once you selected this ln equal to 7, then you can go back to this curve. So for ln equal to 7, you can see the minimum gain, maximum gain. Now you have to choose the the minimum and maximum frequency of operation, so to counter with the line and load regulations. So here you can see the maximum GDC, the gain maximum is and the peak gain is above this line, so it is well and good. So you can see where it is intersecting the frequency axis. So that suppose it is around 0.6 or 0.7, suppose it is 0.7, that you can, if you were using you're using matplotlib, you will directly get the values here, and then which is intersecting this curve. This will be open load condition, so it has to run with the open load also, with the full load also. So for that you take the the maximum frequency, then you'll see where it is intersecting. You can select this particular frequency of for the maximum frequency of operation for your particular design. So in this way you can select this from ln value you'll get q. So from that you can do all the calculations like Guillaume told. But to get this curve, this is the curve that you got in real time. And then after getting your final design value, you can further come back to your model, and you can specify all your design parameters. Then you can go with the sweep for for inner loop. You can do the for current control inner loop. You can design. You can do the AC sweep. You can design your controller. For outer loop, you can do the AC sweep. You can design your controller. So in this way, you can finalize your design in one step with your specifications. So this will definitely save your time. And then to sum up, like, for more than 8,000 simulations, it took less than 6 minutes in 10-core CPU. And we have seen like predictive time step solver and steady state, steady state detection. It helps further to save your time. We have seen how fast it has simulated the 8,000 simulations using our Python API feature at parallel computations. So even though if you are not using multiprocessing or parallel computation, so it will take around 1.5 to 2 hours to complete in a single thread. So that is also a good time for any simulation software if you're running in a single thread also, and that takes 1.5 hour nearly to complete 8,000 simulations. But with parallel processing, definitely it is really good. You can make it run in less than 6 minutes. And you can do the customization of many parameters. We are using scripting, Python API scripting based on your design. As I told you, if you're getting the final curve, if you're there's a chance like if we are not getting that particular values, and if you have to interpolate, so to get the exact thing, you can further customize your parameters. And you can also customize the steady range, that minimum frequency, maximum frequency, what you want to keep it. And the same principle, it can be used for the topologies also. So this is the power of scripting if you are using the Python API, especially with this software. And thank you for your attention. So we can move to the question and answer session. So yeah. Definitely, if you want to try, if you want to experience the same speed and accuracy, you can definitely try this software SIMBA.